We're going to go over one thing we didn't cover last video lecture, and that's going to be the cavity and the layers of the heart. Here within our thoracic cavity, we're going to find a smaller subcavity called the mediastinum. And what we find here are portions of your superior and inferior vena cava, your aorta, and your pulmonary trunk. But also, what's majority of this is going to be is your heart. Oh, I'm sorry, we also find your esophagus, portions of your esophagus in here as well. Now, if we look at the heart, we notice that the heart has this outermost layer. This is called the pericardium. And the pericardium that surrounds the heart, inside to that, we have two different layers. We have, because they're serous tissues, remember we're always going to have a parietal and we're going to have a visceral layer. So this parietal pericardium, this is going to line the inside of this fibrous pericardium. And then internal to that, we're going to find, and we're going to form the visceral layer of the pericardium. Pericardium deals only with our heart. Pleura deals with our lungs. Peritoneum, that deals with our stomach. So you remember all those different terminology from chapter 4. So here, this visceral pericardium, this is actually called another thing. It's called epicardium. So this is that uppermost layer of your heart. It's going to form part of that heart. Right below that, we have the myocardium, and this is going to be composed of cardiac muscle. And then down here we have endocardium, and this is going to form those walls of those internal chambers. Another thing I want you to see here, we have, if you notice the shape of the heart, we have this broad region here and this pointed area here. This is called the base, and this is called the apex. If you look at the lungs, same structure. But of course this is broader, so this is going to be the base, and up here is going to be the apex. Here, apex of the heart is going to point towards your left hip. Base is going to point towards your right shoulder. So make sure you know we have this pericardium housed within your mediastinum of your thoracic cavity. Okay, so make sure you know this for exam number 3. Now for the remainder of this entire chapter, we're going to go over the anatomy of blood vessels. And the very first thing, the very first layer we actually have 3 different layers. Tunica intima is the innermost layer. We have tunica media, which is this middle layer, differs between your arteries versus your veins. And the outermost layer here is going to be the tunica externa. So let's first start off here with the tunica externa. This is the outermost layer. This is composed of collagen fibers. Next layer we have is the tunica media, and this is composed of what type of muscle? Smooth muscle, because we can't control it and it's not found in our heart, so that eliminates the other 2 types of muscles. And this is also, we have elastic fibers here within the tunica media. One thing you want to know about this tunica media is that the tunica media of the arteries are going to be thicker than the tunica media of the veins. So you want to make that note. Now the last layer we have is the tunica intima. This is the endothelium. This is that innermost layer. And we notice here it's composed of 1 cell thick. So it's simple squamous epithelium. And we notice that this tunica intima, that's comprising this endothelial layer, same thing as your capillaries. So we have the same endothelial cells lining your capillaries, also being that 1 cell thick. Simple squamous epithelium. And why is that? We allow the passage of those nutrients and waste, as well as carbon dioxide and oxygen, in and out at this capillary bed. Other things you want to notice, the tunica intima, what lines these within the veins versus the arteries, we have here valves. And we'll see the function of these valves in a little bit, but it's very important that you note we have valves in veins and not in arteries. Now these valves that we see, we also do not see them here within our capillaries. We only see them within our veins. Another thing you want to see is this lumen. So the lumen is kind of space here between the vessel, the innermost region. The lumen is going to be smaller here within the arteries. Smaller lumen compared to the lumen of your veins. It was much wider. And we'll see why that's important when we look at blood flow through these different vessels. Now, we mentioned also another thing about the capillaries. This is where all the exchange occurs. And we can regulate what enters whenever we're going to have this direct blood flow from your arterial to your capillary network, to your venule and back to your vein, or if we're going to allow for exchange to occur. So we'll see that in the next slide. Now, another thing you want to notice here, we have arterioles and we have venules. And these are the intermediate sizes between your larger arteries and your larger veins. Here's a cross-section of our artery and our vein, and remember what accounts for this much wider diameter compared to your veins. Good. This is going to be that tunica media composed, and you notice here is all that smooth muscle. How exactly do we move blood through our entire vessels? And you remember that our vessels, our arteries and our veins kind of function like a highway through our entire body, like shoveling and shuffling around these nutrients, waste products, oxygen and carbon dioxide. And so for the blood to go through our arteries, how is that forced? It's forced through that contraction of your heart. As your heart contracts, it's going to force all that blood through your different arteries. Now what happens then when we're going to go against gravity coming from our lower limbs, how are we going to bring all of that blood back towards our heart? And so our veins are designed in order to accommodate for especially our lower limbs going against gravity. And so this is why we have especially that wider lumen. And so it makes it less difficult for us to pump blood and prevent all that backflow to having it make it more difficult. And another thing we have here are valves. So valves also assist in the movement of blood through the different vessels. And how does that occur? Well, as we move that blood from lower limbs to, through that inferior vena cava, going back towards our heart, if we notice we have these valves that function just like our heart. Anytime you push that blood through, you squeeze that blood through, what's going to happen? It's going to catch that blood, trap that blood here within these valves. So when you are not contracting your muscles, what happens? We can catch all that blood here within these valves. And so the moment you contract your muscle again, you can force that blood through. And then when you relax your muscles, you're going to rest all that blood back onto these valves. Now, the majority of the movement through your veins is what's called milking action of muscles. And if you think about milking a cow, what happens? Well, you pull on mammary glands and also those the nipples of the cows, and so you're physically causing and pushing through all of that milk to come out. Same thing here. If you imagine your muscles, as you contract your muscles, what happens? You're contracting your muscles, you're going to squeeze along the walls of your veins, and you're going to force blood through one direction. Why is it not going to go in the other direction? Because once again, we have these valves. The valves are going to collect all that blood trying to go backwards. And as you contract your muscles, you're going to force that blood through back towards that heart. When your muscles relax, you're going to catch it along these valves. And so that's why it's really important when people say you got to exercise, because by exercising, you really help the flow of your blood. You're allowing your blood more circulation, and you can contract your muscles and push those blood through your valves. Now, of course, both of these arteries and your veins have those smooth muscles. And so those smooth muscles in turn, so we'll just put that over here, smooth muscles, also can contract. So they're also going to undergo contraction and move your blood along through your vessels. Let's now take a look at the different capillaries comprising the capillary bed. We're going to start off by looking here. We have this arterial, and here we have the venule, so returning to the heart, and here we going towards our capillary bed. I want to look at a couple of structures to show you. Here we have the precapillary sphincters, and what this is for, these sphincters. When they contract, we're going to notice that it's going to allow the blood flow to come directly from our arterial to our venule. And so because of this, we have two different types of capillaries. We have what's called the vascular shunt, which is this direct flow of blood from your arterial to your venule. And then we have the true capillaries, and the true capillaries are over here, and this is where we have all the exchange occurs. So exchange of both waste and nutrients. And the vascular shunt, once again, is going to bypass all of this exchange when these precapillary sphincters are constricted. And so when they contract, they're going to close off all that blood flow at these capillary beds. Now, when can you think of incidences where we want to have direct blood flow from your arteries, arterioles, directly to your venules, and you want to bypass any exchange to occur? Good. So a couple of times first you have in your digestive system. And so for your digestive system, this is especially going to be true in that sympathetic or parasympathetic nervous system. Very good. In your sympathetic nervous system response, that fight and flight response, you're going to decrease digestive activities. And so when you decrease digestive activities, here at this terminal arterial end, these sphincters are going to constrict, and we're going to reduce blood flow here going into your intestines in order for you to decrease your ability to start digesting food. And that way we're going to direct all that blood flow and bring that towards, we want to bring it towards your liver to break down glycogen into glucose. You want to direct all that blood flow towards your lungs for respiration. And here we can have the lungs at the capillaries. And so when we look at that, when we have that sympathetic nervous system under firing, if this is going to be our lungs, all of this is going to be relaxed. So we can have increased flow there in that area. When is another time you're going to have this blood flow directed from your arterial end to your venular end? What other times can you think of? Good. So not only your intestines, but also your stomach. So another thing for digestion, right? So you definitely always want to engage all the muscles. So you're going to have, of course, more of this is going to be dilated for your skeletal muscles when you're going to use that sympathetic nervous system. Here is an overview of the different types of capillaries. So, of course, you can have lots of vascular shunts all throughout your entire body, allowing for blood flow to be increased and then also decreased. Okay, so you can just be familiar with this. However, you don't need to memorize all of this entire picture. I just put this up here so you can have an understanding of the different capillary beds, just a couple of the different capillary beds we have in our body. However, we are in the next few PowerPoints, we're going to go through the different arteries, the different veins, and so this is a great overview of what we're going to be going through. So let's start off by going over the major arteries of your systemic circulation. And the very first one that we're going to look at is the aorta. And the aorta is the largest artery in the body. And the aorta, once again, stems from our left ventricle. Let's just cut that in half. So from here, our left ventricle, when we have the contraction of our heart, we're going to force that blood here to our aorta, and that's going to go to the rest of our body. And our aorta is going to be broken down into different regions. We have the ascending aorta, so that's the initial region over here when our aorta is going up. When it arches towards the left, this is the aortic arch. And then when it descends, this is going to be the thoracic aorta. And the thoracic aorta is the descending region after our aortic arch and above our diaphragm. Now, once we cross our diaphragm, we're going to enter into the abdominal cavity, and that's when the aorta becomes the abdominal aorta. So down here is going to be the abdominal aorta, and here's that diaphragm. Here's a closer look. The left ventricle, we have the ascending aorta, aortic arch. Going down, which we don't see, this is going to be now the descending aorta. And then once we cross that diaphragm, going to be the abdominal aorta. Now, blood supply stemming off of this ascending aorta, we saw this last time. We have that right coronary artery, and we have the left coronary artery. So that's going to come right off of here. And those are the only arteries that stem off your ascending aorta. So ascending aorta, we have the right and left coronary arteries. Let's now focus on this next region, the aortic arch. And from here we have three different vessels that stem off: the brachiocephalic trunk, and then we have the left common carotid artery, and then the left subclavian artery. From this brachiocephalic trunk, we have two other divisions of the vessels. We have the right subclavian artery, and we have the right common carotid artery. And so that right subclavian artery is going to be this artery over here. And this is going to be the right common carotid artery. Now from here, this right common carotid artery, and this is going to, from here, it's also going to be mirrored on your left common carotid artery. We're going to bridge up, or come up here, and we're going to feed our neck and our head, so all the tissues and muscles in this region. And so from this right common carotid artery, we have a branch, and this is going to be your right internal carotid artery. So on the other side, it's going to be the left internal carotid artery. Now from here, this internal carotid artery, this is going to feed into our skull to deliver all that oxygen and nutrients to our brain. So from that internal carotid artery, we're going to divide into both the anterior and middle cerebral arteries. And both of these arteries are going to give the nutrients to our cerebrum. So we're going to pause here and look at that illustration. Here is that middle cerebral artery. Here is that internal carotid artery, both from our right side and from our left side. And so this is going to feed here into that middle cerebral artery. And it's going to form here into this anterior cerebral artery. And once again, this is going to feed all of those tissues comprising our cerebrum. Now let's take a look at these vertebral arteries. That's going to form the basilar artery, and this is going to feed all the brainstem and the cerebellum. So let's take a step back and see where that vertebral artery is from, and it actually stems from that subclavian artery. So whether it's right or left, and here is that right vertebral artery, and it's going to feed back here to supply those nutrients. Now let's take a look at what they look like. So here's that vertebral artery coming together from both your right side and the left side, and we're only forming together to combine to form one basilar artery. Now, next area we have is the posterior cerebral artery. This is a division from the basilar artery, and it's going to supply the posterior cerebrum. And so here is that basilar artery, posterior cerebral artery. If you notice here, giving nutrients to the posterior aspect and region of the entire brain. And then once again, the middle cerebral artery giving nutrients to the middle region of the brain, and anterior towards the anterior region of the brain. Now if we notice, we can also see what's forming that looks like this nice circle, and that's formed by both the anterior and posterior blood supplies that allow this nice communication and network of blood vessels. And so we call that the circle of Willis, and that's formed by both this anterior cerebral artery and this posterior cerebral artery. And so if you look, it kind of looks like the head of a guy named Willis, nice mouth, there are his arms and his legs, so happy. Here is an illustration of the different arteries comprising our brain. And of course, you will also have a list of all the different arteries you'll need to know for your exam. Now, we looked at those branches stemming off of this brachiocephalic trunk. So whether it's going to be your common carotid artery or your subclavian artery. And here we have that left common carotid and also the left subclavian. And so once again, three major branches from that arc of the aorta: brachiocephalic trunk, common carotid, and the subclavian. Now let's take a look at the branches from this brachiocephalic trunk. From here, we're going to enter into the right subclavian. Sub, once again, meaning below the clavicle, and here is that clavicle. So here is that region right below. This is that right subclavian, Then we have axillary, which means what? That underarm area. So once we reach this area, it's going to be the right axillary. Brachial means arm. So now we're in the brachial region. Radial, remember our radius is this bone that's the outermost, facing the most distant from our body. So once we enter this region, we're going to enter the right radial artery. From our aortic arc, now we're going to enter into the thoracic aorta. And so from here, we have lots of arteries that stem off this thoracic aorta. We first have intercostal arteries. This is going to supply all those muscles and tissues lining our thoracic cavity. We also have arteries that supply our bronchi, our esophagus. It's going to be for our digestive system, and our diaphragm to assist us with respiration. Now from here, once we cross this thoracic region, entering here, we're going to have the abdominal aorta. And this is a great illustration of the branching from this abdominal aorta. And so as we descend along this abdominal aorta, the very first branch we have here, this is called the celiac trunk. And so celiac trunk is going to branch off into three major arteries. We have the common hepatic artery. Hepatic deals with liver. So this is going to be the one that's going to go feed and give nutrients towards our liver. We also have here the gastric. Gastric means stomach. So this is our left gastric artery. And then finally here we have the spleen. So we're also going to filter our blood through the spleen. And the function of that spleen is to filter out any dead, dying, or worn out red blood cells. And so from here you're going to notice, we'll get into that when we go over the veins, but these blood supplies are going to feed back into your liver. Now, another branch that we have from this abdominal aorta is going to be the superior mesenteric artery. So here's this abdominal aorta still going down. And then another branch, here's that superior mesenteric artery. This is going to supply most of the small intestines and the first half of the large intestines. Then from here, we're going to keep on branching down for our lower extremities. So from that abdominal aorta, okay, so here we're going to have that branch. What we terminate with, so another branch, we have inferior mesenteric artery. This is going to feed this lower half, so the second lower half of the large intestines. So second blood supply for your large intestines. Now here what we're going to terminate with at this abdominal aorta is we're going to have this branch. And we have what are called the left and right common iliac arteries. So here we have our right common iliac artery. We have our left common iliac artery. Now you'll notice as we branch over here, we have another branch that stems off. And this is going to be the internal iliac artery. And this is going to serve all of your pelvic organs. From here, we're going to go into the external. So this is an internal, and this is an external. So external iliac artery, and we're going to enter our thigh. So this is going to be the femoral artery. From here, we're going to branch off. Here we have the popliteal. So popliteal is being the one right behind that knee. And then we also, from here, we're going to branch off into both the anterior tibial. So tibia is that big T-shaped bone. So anterior, and we have a posterior tibial artery. Now, only this anterior tibial artery, that's going to branch off. So let me just clear that really quick. From this anterior tibial artery, we're going to form the dorsalis pedis. So this is a dorsalis pedis artery. And then finally, we're going to terminate at this region over here, these arteries, and this is the arcuate artery. Now, what happens on the other side? We're going to have veins. Let's take a look at how we bring that deoxygenated blood back towards the heart. And so all that return is either going to come from the head the neck and the arms through the superior vena cava. Or if we're talking about the trunk of our body and our lower extremities, that's going to come into our heart from this inferior vena cava. Now, where they're going to enter into the heart is going to be this right atrium. And what we're going to take a look at for the rest of the slides are the different veins that feed into, starting off with the superior vena cava. First, we're going to look at this venous return coming from our arms. And so we have the right radialis, right ulnaris. This is going to feed into that right brachial vein, and this is going to drain into that right axillary vein. And then we're going to feed this into that right subclavian vein, into that superior vena cava. Now, what about all of the superficial tissue? And so this is going to, so for example, our skin, and also those adipose and all those other blood supplies giving nutrients to those tissues surrounding our superficial tissues. We have the cephalic vein for that. So this is going to drain the lateral aspect of the arm. And so here's that cephalic vein right over here. And eventually this is going to feed into our axillary vein. Now, basilic veins, this is going to drain the medial aspect of our arm. This is going to drain into our brachial vein. So here's our brachial vein. And then that in turn is going to drain into our axillary vein. From here, what are the other ones that we're going to look at? So axillary vein, this is going to feed into our subclavian vein. And also what else feeds into the subclavian vein is this external jugular vein. Here's the external here. And also this external is going to feed into the subclavian vein. And this is going to drain our head into bringing all that venous return back from our brain and all the tissues within our head and our neck. The other veins you should know, here we have the internal jugular vein, and this is going to be draining the sinuses of the brain. And then here we also have the brachiocephalic veins, both your right and your left, and these are going to receive blood drainage from your subclavian, your vertebral, and your internal jugular vein. And all of these collectively are going to flow into your brachiocephalic. Brachiocephalic goes directly into your superior vena cava. And so that's all written for you over here. So make sure that you do know the 3 different venous blood returns that feed into your superior vena cava. Now, another vein that you should know is the azygos vein, and this is a vein that drains your thorax. And this is that only vein, it's a single vein that drains the thorax. And it's also going to drain into your superior vena cava. And here's this illustration. Here's that azygos vein feeding into that superior vena cava. This is not found in your textbook, and it just helps you understand the different veins feeding into the bigger veins, and it's just this nice flow chart. You don't have to memorize all of these veins if they're not going to be on your terminology list. So just look at your terminology list to look at the ones that you specifically need to know for exam number 3. Now let's talk about this inferior vena cava and what drains into that. And so we have gonadal veins. This is for your gonads. It's going to drain your ovary in females, and if you're in males, it's going to drain your testicles. We also have the renal veins. Once we filter all that blood through our kidneys, we need to return it back towards our blood flow, so it's through that renal vein. And this is a very special one called the hepatic portal vein that drains the digestive organs. So it's not only going to digest and bring back deoxygenated components, but it's also going to bring back nutrients to bring into your liver. And so other veins that we have, we'll go into that hepatic portal vein in a little bit. Let's take a look at this lower limb. And so from this lower limb, you have a couple of veins you need to know. We have this great saphenous vein, which is this vein over here. And this great saphenous vein is the longest vein that you have, and it's going to drain that superficial of regions of your legs. And we're going to bring it all the way from this dorsal venous arc all the way down to your femoral vein. Now, other areas we need to know, we have the posterior and anterior, so anterior and posterior tibial veins. And this is going to feed into your popliteal. So here is the popliteal right behind that knee. Then you have the femoral. Then you have the external iliac, internal iliac, common iliac. Looking at the veins that during your lower limb, we have this long vein. This is the longest one in our body. This is a great saphenous vein that originates from the dorsal venous arc. This is going to feed into your femoral vein. And here is that femoral vein. It's going to form into this popliteal vein. And then we also have the anterior tibial vein and the posterior tibial vein behind it. Better illustration over here, that was just to show you all the different pathways of how they feed into each other. So once again, once we have capillary exchange down here within our foot, we're going to bring back that venous return, starting at this dorsal venous arc. Bring that into the great saphenous vein if we're looking at superficial drainage. Now here we're also going to drain at our anterior tibial vein and our posterior tibial vein. Both of these are going to converge at the popliteal vein. Popliteal vein right behind your knee is going to form into the femoral vein. And of course your great saphenous vein is going to feed into this femoral vein. This is going to feed into the external iliac vein. Here's your internal iliac vein. They're going to converge right over here to form your common iliac vein. Now both of these collectively, both your right and your left, are going to form the inferior vena cava. So inferior vena cava is going to enter into which chamber? That right atrium. If we look at the circulation in a fetus compared to an adult, we know that they're very different. And so in a developing fetus, we're able to give direct oxygen from our mother's blood into our fetus as blood is able to cross from the mother through the placenta. And really the placenta is this sac that's able to, where nutrients and oxygen is able to cross through. And because of that, we don't need the use of the lungs, nor do we need the liver to break down all those nutrients for the developing fetus. And so fetal circulation, the function of this is to allow a one-way system flow of blood through the fetus that will bypass the lungs and liver. Okay, we'll start off here from the placenta. We're going to enter into the umbilical vein. So umbilical vein, this is filled with oxygen-rich blood. And this oxygen-rich blood, instead of going into our liver, we're going to merge directly with our inferior vena cava. And now from here, we're going to bypass the liver through the structure called the ductus venosus. So ductus venosus prevents blood flow through the liver. And that way our liver is not filtering anything yet. We're not filtering any of that blood just yet. And now we're going to enter to our femoral inferior vena cava. We're going to enter into our right atrium. Now from our right atrium in an adult, where do we go? Good, we go to the right ventricle. And when the heart contracts from that right ventricle, where do we go? We go into the pulmonary trunk that's going to go into our lungs. Now here, what's under normal circumstances, that's what happens. But in our fetus, what we have is a structure that prevents us from even trying to bring all of our blood to this pulmonary trunk because we don't want to even go to our lungs. So rather than dealing with our lungs, we're just going to create a direct passage from our right atrium to our left atrium. And so we can't see it, but here in this interarterial septum, we have this hole that connects these two chambers together, and that's called the foramen ovale. So foramen ovale, this connects the right atria directly to that left atria to bypass the lungs. In the event that we do have blood that goes from this right atria to the right ventricle and we have contraction, what's going to happen, that blood's going to go to the pulmonary trunk and it's going to want to go to our lungs. Well, in this instance, let me just clear this off really quick. We can also bypass any blood that enters into this pulmonary trunk, and that's done through this ductus arteriosus. And so blood that enters here is going to get fed into the aorta. And once it goes to the aorta, where does the aorta go? It goes to the rest of the body. And so in a fetal circulation, actually let's just write this first. So ductus arteriosus is able to collect and we can just say dump in quotation marks the blood from the pulmonary trunk I can spell, into the aorta. Okay, so the aortic arch specifically. Now, I'm going to clear this one more time and let's go over the entire circulation. And this is something that's going to be key for exam number 3. And so we're going to come from the placenta, bring oxygenated blood and nutrients into the fetus through this umbilical vein. We're going to bypass our liver using this ductus venosus, and we're going to bring that blood and merge it directly with our inferior vena cava. From this inferior vena cava, we're going to enter into our right atrium. The right atrium is going to bring that blood directly to our left atrium. From our left atrium, it's going to be exactly like the same in an adult heart. We're going to bring that blood into this left ventricle. Left ventricle is going to push that blood into the aorta. From that aorta, we're going to go into this descending aorta. Then we're going to bring back all that deoxygenated blood through this umbilical arteries. Okay, so that's the circulation of our entire body, or in the fetus. Now, in the event that any blood coming from our right ventricle enters into our pulmonary trunk, we can relieve all of that blood and bring it directly into our fetal circulation once more by the structure called the ductus arteriosus, and that's going to bring blood into this aorta. It's going to feed into the rest of the body. Now, of course, we also have the external iliac artery, internal iliac artery. All these other arteries and veins are going to feed into the body, and at the capillary bed, we're going to bring it back up to this inferior vena cava and then drain it out through the mother. One of the most important veins in our body is this hepatic portal vein, and that's because it's going to drain all of the intestines and our major organs through our liver. And our liver, of course, is that one detoxifying organ. And here's this overview. I like this illustration just because you can see all what feeds through your liver. And so if you remember, from this illustration here, we have celiac trunk breaking here into this common hepatic artery. That's just going to give the nutrients to supply this liver and the tissues of that liver itself. But of course, we also have a blood supply through our stomach, our spleen, our intestines, and our lower extremities. And if you notice, here within our intestines and our stomach and our spleen, we're going to drain all of these contents through this one vessel over here. And this is called a hepatic portal vein. And so right after you digest your meal and all of your foods, we're going to screen and store all of that here within your liver. And so liver, very important, not only for detoxification, but also storage of a lot of those nutrients. And once it screens and goes through whatever is getting filtered through your liver, it's going to return its flow into this inferior vena cava. Here's another illustration of that. Okay, so here you have your intestines, your stomach, and your spleen all feeding into the hepatic portal vein. And hepatic portal vein is going to feed into here. So you can see it entering into your liver, and the other side is going to be your inferior vena cava. Now this is interesting because notice it's a vein feeding into another vein, and this vein is entering into an organ. Typically we've seen arteries that go to capillaries that go back to veins. Okay, and so with this one we have arterial flow, all these nutrients, oxygenated blood. It's going to go here into your stomach and intestines. We're going to absorb those nutrients, toxins. All of this is going to get sent off since it's deoxygenated already and we've already screened it. We enter into this hepatic portal vein. Hepatic portal vein is going to enter into your liver, and so it's a vein entering into an organ. Screen it, store nutrients, get rid of those toxins, and then deliver all that back to your inferior vena cava. So remember this system. The next topic we're going to look at is the pulse. And as our heart contracts, it's going to expand our vessels and it's going to then relax them. And of course, we can feel this the most in our arteries because our arteries are the lumen is much smaller. And this is where we pump all that blood out directly from that aorta. And so as those arteries contract and expand and then recoil and relax, we can feel these expansion and recoiling at certain pressure points. Okay, so a pulse, what that is this pressure wave that's created by the expansion and relaxation of those arteries. Now, pulse average is about 70 to 76 beats per minute at rest. And so looking at these pressure points, where do we find them? The superficial temporal artery, facial artery, common carotid artery. Great areas, right? Once you leave that heart, you can definitely feel that common carotid artery. Brachial artery, radial artery, femoral artery, popliteal artery, posterior tibial artery, and your dorsalis pedis artery. Now, how does this differ from blood pressure? As that blood is then forced, as we contract our heart, and you force that blood through your entire arteries, you then can generate a certain amount of pressure against your vessels. And that's what blood pressure is. And so we can measure it by when our heart is in contraction. So that's systolic. Systolic deals with contraction of your ventricles. You can also look at the pressure exerted within your arteries when you're in relaxation. So this is diastolic. So when your ventricles are relaxed. Now this term systolic in general means contraction, diastolic means relaxation. But when you look at your blood pressure, you're looking at the ventricles. So the pressure exerted by the ventricles, whether it's contracted or whether it's relaxed. And of course, the farther away we are from our blood vessels, from our heart, our blood vessels, the pressure is going to be decreased. So it's going to decrease in pressure the farther away we are from our heart. So as the heart distance increases. Let's see what that looks like. Okay, and so looking at those arteries that we just learned, here we know in our aorta is going to branch into so many different arteries. And because we're going to start branching, all that pressure is going to be distributed to all these different vessels. Now from here, we're going to enter into our arterioles. And arterioles, they spread even further. So here's our aorta. We're going to branch into arteries. Arteries itself are going to branch into arterioles. Now from arterioles, we're going to branch into capillaries. Now look at all that surface area we've created. So from a lot of pressure, so high pressure here. We just came from our heart. So look at all this distance that we've expanded. And because of that, the farther away we are from the source, the lower the pressure is going to be. Now of course, capillaries is going to be very small vessels compared to your arteries and your veins. Venules, we're going back towards our heart, then you have your veins and then your vena cava. And of course, by the time you reach your vena cava, We are farthest away from our heart, so we have the lowest pressure. How can we measure the blood pressure? Okay, so we can measure them actually by even looking at your brachial artery. This is one common area that we look at it. And so what's common is blood pressure that's a systolic of 120 mmHg. mmHg means millimeters of mercury over 70. So when we write blood pressure, it's the systolic over the diastolic blood pressure readings. Now, this is considered in a normal adult. So we're going to, whenever you take your blood pressure, whenever you start using, we use this a machine or this instrument called a sphygmomanometer. And so what this is going to do is going to be able to determine what our blood pressure is when our blood vessels are contracting and during relaxation. So the very first step is to use this band. You're going to cut off all that circulation to your lower limb. We're focusing here on this brachial artery, so we're collapsing it and we're closing it. Now, because normal systolic pressure is 120 mmHg, we're going to pump that cuff above 120 to ensure that we cut off the entire circulation. Now, you also want to make sure you don't hear any blood flowing through towards your lower arteries. Now, you're going to slowly release that pressure in your sphygmomanometer, and that's going to allow, eventually you're going to hear a tapping sound. So this tapping sound is some blood that's starting to drip through from the pressure that's cut off into your lower limb. So your lower arm, I mean. So here's going to start dripping through. And the moment that you start hearing that blood dripping through, that's going to be your systolic pressure that you're going to record. Now you're going to gradually continue to allow more air out. And the moment that you don't hear any more tapping, so actually I can let you hear it. It goes like this. And then eventually you're not going to hear any of that tapping anymore. And the moment you don't hear any of that tapping, that's going to be your diastolic pressure. And so diastolic pressure, this is when your heart, the amount of pressure exerted on your vessels during ventricular relaxation. And so that's when eventually whatever reading that's going to be in your denominator. Okay, so that's how you get blood pressure. Now, this is something that we looked at last chapter, looking at blood pressure affects different factors. Blood pressure, of course, is affected by your age, your weight, the time of day. Of course, if you're resting, it's not going to be as high compared to you exerting a lot of pressure all day long. If you've exercised, your body position, laying down versus standing up. And also, let's take a look at other terminology. So this we saw already, cardiac output, the amount of blood pumped out of your left ventricle per minute. And then peripheral resistance, if something has resistance, it's being able to prevent things from flowing very smoothly. And so this is a friction encountered by blood as it flows through the different vessels. How do you change your blood pressure? You can look at your cardiac output and your peripheral resistance. If you have a lot of peripheral resistance, your blood pressure is going to be much higher. Okay, other factors of looking at blood pressure, we looked at this already, your sympathetic nervous system versus your parasympathetic nervous system. This is going to increase your blood pressure, especially in terms of fight and flight response. Renin is going to adjust and alter your aldosterone levels, thereby, once there's aldosterone due again, it's going to take in more sodium, and in turn, water is going to follow. It's going to increase your blood volume and therefore increase your blood pressure. Anytime you have high blood volume, you're going to have a high blood pressure. Temperature, if we look at temperature, heat, vasodilating effect. And if it's cold, it's going to have a vasoconstricting effect, which also is going to allow and regulate how much of that blood is going to be able to flow through your vessels. And then, of course, we have chemicals and your diet. And so aspirin being that dilator, and also a lot of the pills that you take have different effects on your blood pressure. Here's this illustration of the different factors that can give rise to increasing your blood pressure. So once again, those chemicals, increasing resistance. If you don't drink a lot of water, you have lots of viscosity within your blood, also increasing that resistance. Stroke volume. How do you increase stroke volume and increase your heart rate? You can stimulate your sympathetic nervous system, increasing your cardiac output. And of course, cardiac output, once you increase this, you can also alter your blood pressure. Now, looking at normal human ranges for blood pressure, normal we have 110 to 140 millimeters of mercury. And then for diastolic, we have 75 to 80. Hypotension, hypo meaning below. This is when your systolic is below 110, typically associated with illness. Hypertension, lots of people have hypertension, and of course you want to take hypertension medicine, increase dilation, and also decrease that volume retention. And so this is when your systolic pressure is above 140 mmHg. Now, the last thing we're going to cover is this capillary exchange, because capillaries, of course, are where we have all the exchange of nutrients, oxygens, and waste products. And so all this can be done by its concentration gradient. Remember, diffusion, something from a higher concentration is always going to go towards a lower concentration. And so we have different mechanisms of exchanging nutrients and waste products between your tissues and cells in your capillary bed. We have direct diffusion across your plasma membrane. We have endocytosis or exocytosis. This is typically done with larger proteins. Proteins in itself cannot easily cross through our membrane. We have gaps, which are called intracellular clefts. And we have pores, which we call fenestrations in some capillaries. Let's go over these 4 different ways of transport across the membrane again. These are direct diffusion through the membrane. You'll see this of the gases. Also, diffusion through intracellular clefts. These can be ions. Same thing through the pores. You're going to see lots of ions and fluid through this area. And of course, the larger molecules and larger proteins are going to need to be transported in and out through the membrane. So this is transport vesicles. And we use endocytosis and exocytosis for that. Now, let's look at what exactly drives this pressure that allows the fluid to go from the vessels into your tissues and cells, and also the opposite direction. And so what we're going to have is we're going to have blood pressure that's going to force all that fluid out of your capillaries. Remember, we're coming straight from our heart, so we have more pressure coming from our aorta to our arterioles to our capillaries compared to the other end. However, since we have low blood pressure coming into our venules, what can we use then? Well, we have osmotic pressure. Drawing in fluid back into our capillaries. Okay, so we're going to have higher blood pressure than osmotic pressure at our arterial end. And we're going to have a lower blood pressure but higher osmotic pressure at our venous end, and that's going to allow the return of those waste and carbon dioxide back into our systemic flow. And so let's look at this. Here is normal levels of osmotic pressure. This is what's found in our capillary bed. Now here we're coming straight from our heart. So here we have lower osmotic pressure compared to blood pressure coming from our heart. So what's going to happen at this arterial end, we're just going to draw this directly in half. At this arterial end, all this blood pressure is going to force oxygenated blood and nutrients out of our capillary bed. It's going to enter into this interstitial fluid, and eventually it's going to enter into our tissue cells. Now coming back after our capillary bed, now our venular return, what's going to happen here? So our venous return, osmotic pressure, this is normal levels. Blood pressure is going to be lower, we already know that. And here we have, because our blood pressure is lower and we have more osmotic pressure, what's going to happen? We have lots of fluid here compared to our vessels. So all that fluid is going to come right in. Remember, osmosis deals with only that movement of water. So we're only going to move those water in here. Now with the movement of water entering into this direction, what also can we carry with it? We can carry it with the gases. Waste products, higher concentration of waste inside of the cell compared to the capillaries, that can also move from the cells through this interstitial fluid back into your capillary bed by exocytosis and endocytosis. So we're not going to move a lot of those nutrients when we deal with osmosis, but we can by the membranes infusing, pinching off, and engulfing it and bringing it into the cell. Okay, so this is very key. Also, something very important to know for exam number 3 is that the driving factor to bring nutrients out is going to be blood pressure, bringing deoxygenated blood back in, and also bringing back and maintaining that blood volume is going to be osmotic pressure. And so that's it, and that's the end of chapter 11.